Welcome to our first lesson on the Doppler effect. We'll be looking at the theory behind the Doppler effect today. Now the definition for the Doppler effect, and please make sure that you memorize it off by heart as it is the apparent change in frequency of a source of sound if there is relative motion between the source of the sound and the observer. So from this you'll realize that we're going to be having an observer, which is then going to be my listener, and then we're going to have a source which is going to emit, in this case, a sound. If there is motion relative to these two objects, then we will have a change in frequency. Now we're going to explain this change in frequency making use of wave fronts, but let's just first see again, what does a wave front mean? Now if you look at our normal transverse waves, and we view them from above, then we would note though that all the crests, which is obviously your highest points over here, will just be seen as straight continuous lines. In between these crests there would be troughs, which I'm indicating here with a dotted line, but you would actually not be able to see them because you won't be able to see the depth into which they fall downwards. So therefore you will only be able to see the crests, and they are then seen as these straight continuous lines. Now remember again that these crests are in phase, which means they move at the same position at the same time. And therefore, two consecutive points that are in phase, like my crests, which is then indicated by these two straight lines, this is also then seen as the wavelength. Now let's just first go again to what is the specific definition for a wavefront. So the specific definition for a wavefront is an imaginary line joining all the points in a wave that are in phase. And these points specifically we refer to as crests, and they are thus in phase to each other. Now we have spoken about wavelengths, but just to define them again, remember wavelength is seen as a symbol Greek of lambda, and it is known as the distance between two successive wave fronts, and we measure this always in meters. Now we will also be referring to frequency again. Frequency has got a symbol of a small letter f, and it is known as the total number of waves per second, and the unit in which we're going to be measuring frequency is known as hertz, or it can also be seen as per second. Now when we are looking at the frequency and the wavelength, we can usually from that go and calculate the speed of a wave. Now this speed of the wave is indicated here by the v, and this speed will stay constant within a medium. That means while I'm talking, for example, my sound wave will stay constant in the speed. On the other hand, if I was though talking from outside, let's say in air, to somebody inside the water in a swimming pool, then I would have a change in medium. It will go from air, in this case, to water, and then there will be a change in speed. But as long as I keep it to one medium, then the speed will stay the same. So what will happen in this case? We will in most of our situations have one medium only, which is most probably going to be air. So that means the speed must stay the same. If I though have a change in my wavelength, let's say the wavelength increases, remember I still need to get back to the same speed, then my frequency needs to change in such a way so that we end up again with the same speed. So if my wavelength increased, then it would mean my frequency needs to decrease. And from this we will realize that my frequency is going to be inversely proportional to my wavelength, which means if the wavelength increased, the frequency will thus decrease. And if the frequency increased, then the wavelength will decrease. So that's the type of relationship that they will have in order to ensure that we will always have the same speed. Now in grade 11 you've learned that frequency refers to the pitch when we look at sound. And pitch on the other hand refers to how high or low a note would be. So typically if a child is screaming at the top of their lungs, it's a very high pitch. On the other hand, if you have your older type of person talking, specifically your grandfather, then it's a low note, which means a lower pitch. So our frequency thus would be a high frequency means a high pitch, which means in this case a high note. If we though have a low frequency, it means a lower pitch, and this case then refers to a lower note. Now yes, you would refer to as high and low notes sometimes as a louder sound for a high pitch and a softer sound for a low pitch. That's just how you might be observing it. But as said, it all depends on the frequency. Now we're going to start off by looking at a stationary source. Now here is my ambulance, and in this case it's got a siren on, and that then is going to be the source of the sound. Just source just means the origin, the place where the sound actually starts. So if you're talking, you are a source of sound. Now you'll see that I have wave fronts that's emanating. That means that is in this case going out in all directions from this source of the sound. Now as said, if this object is stationary, then you would take note though that this wavelength that is indicated between the distance of two wave fronts stays the same on either side. So my wavelength in the front is the same as that of the back, and therefore wherever you are standing, whether you are now standing in front of this source or at the back of the source, you would still hear the sound at the same note. That means in this case the same frequency, independent of whether in the front or the back. But now let's go over to the situation where the source of sound is going to be moving. So let's consider a situation where this source of sound is now moving towards you. Now you would note though that now as it's moving, it is going to move into its wave fronts. And when it moves into these wave fronts, which we saw when it was stationary, then it compresses them right here in the front. And it basically then means if it compresses them, that means put them closer to each other here in the front, it would mean that they get stretched out there at the back. So if we're going to go and compare our wavelengths, our wavelength here in the front is now far smaller than the wavelengths here at the back. Our wavelengths now at the back of this specific source is longer, and those in the front is shorter. Now note though that you in this case are standing in the front. Now we want to know, are you going to observe a different frequency than what this specific source is actually emitting? The answer is going to be yes. The reason being, this wavelength that is now shorter means it is a greater frequency which is now being emitted. Now remember, the frequency though by the source is still going to be the same. The only difference is you are going to hear it differently. So although the source still has the same frequency as what it had originally, you'll be hearing it differently. Now let's just quickly go back again to your first scenario where the thing was stationary. Let us just for our example's sake say that this source had a frequency of 1000 Hertz. And because it was stationary, whether you were standing in the front or at the back, you would still hear the sound as 1000 Hertz. Even though he is in this case not moving, he's admitting it as that, you are hearing it as it. But now that he is moving, he is still emitting 1000 Hertz, but you will now be hearing a higher frequency than 1000 because the waves are shorter in the front, which is inversely proportional to the frequency, which means a higher frequency. Thus you will in the end hear a specific frequency that will be greater than 1000 Hertz. Now let's go and look at the scenario when you're standing behind the source. Now the source is moving away from you. Once again, he compresses the wave fronts in the front, therefore the wavelength becomes shorter, but the wavelength at the back becomes longer. Now if this specific source is still emitting a sound of 1000 Hertz, note though that a greater wavelength means a shorter, or in this case a lower frequency. And a lower frequency means a softer type of sound that you'll be hearing because the note is going to be lower. So if you're standing at the back, you will actually hear this at a lower note. So that means less than 1000 Hertz. And the reason being because the wavelength is longer, and that means to a decreased frequency. Now you might have heard this many a times before, if not every single day. So if a car is moving towards you, let's say he's blowing his hooter, then you will be hearing the sound as a higher and higher note when it approaches you. But when he moves away from you, then you hear it as a lower note. So let's just quickly recap. If the object is stationary, then whether you're in the front or the back, you will still hear exactly the same frequency as what the source is emitting. If you are standing in front of the object when it's moving towards you, you're going to hear a higher frequency than what the source is actually emitting, because the wavelengths in the front get compressed, and that means, in this case, a higher frequency. So therefore you hear a higher note. If the source moves away from you, then you will be observing a lower note, because the wavelengths are longer, which means a shorter frequency, and that actually then contributes to the lower note that you're hearing. And that's typically what blind people will also be making use of. Because they cannot see an object coming, they are making use of their hearing to hear, is this specific frequency coming towards me, meaning is it a higher frequency, or is it a lower frequency, which means it's moving away from them. Now in all of our examples, we are going to be looking at a situation where you're either standing right in front of the object or right behind the object. That means basically in the path which the object is traveling. And that would mean, if this object though is, let's say, 200 meters away from you, as said, because it's approaching you, the wavelengths in the front are shorter, which means in our case a shorter wavelengths referred to a higher frequency, and that means you will hear the observed frequency as higher. Now let's just say once again that this source is 1000 Hertz and it's approaching you. Because it's approaching you, you're going to hear it at a higher frequency, and you hear this as a frequency of, let's say, 1050 Hertz. Now, it doesn't matter whether this object is 200 meters away from you or he's so close to you that he's only 2 meters away from you. You would still only hear the frequency as 1050, independent of how far away it is from you. This observed frequency by you has got no relation to the distance it is away from you. Now you might tell me, yes, but usually if an object is sometimes approaching you, you are not hearing it at the same constant note, whether it's 200 or 2 meters away from you. It sounds like it becomes louder. So it's a typical situation where you hear it like a racing car driver. It sounds like it's coming towards you, but it actually sounds like the sound is becoming greater and greater. Now that's due to the fact that you are not standing directly in the path of that source. You are actually standing on the side of the source movement. And therefore, because you are at an actual angle to this movement of the object, that's how come you hear it as a sound that becomes louder. But it is actually not that situation when we are going to do our calculations. We'll be only doing the calculations when you're standing right in front of it. So when it is approaching you, you'll still hear it as a constant frequency of, in this case, 1050, independent of how far away it will be from you.